Welcome to Networks Professionals.
All right, let's dive right into this explainer of our source material on local network communication. Today, we're demystifying the Address Resolution Protocol, or as it's better known, ARP. You know, if you're managing networks, configuring systems, or even just trying to troubleshoot why your Wi-Fi is acting up, you probably know that bridging the gap between logical routing and the actual physical hardware is absolutely essential. Well, ARP is the silent workhorse that's literally making all of that happen right behind the scenes.
So think about this for a second. How do devices actually find each other on a local network? We all know that at the network layer, routing relies completely on the IP addresses. But when you get down to the physical cables and the radio waves, switches and network cards are operating strictly on hard, physical targets. They don't care about your logical IPs at all. So the real question we have to answer here is, how do these devices dynamically map those logical IP paths to actual physical endpoints out there in the void of a local network?
Basically, we're dealing with two totally distinct addressing schemes here. It's like a massive language barrier. On one side, you've got these dynamic 32-bit logical IP addresses hanging out at the network layer, and on the other side, you've got the fixed 48-bit physical MAC addresses that are burned right into the network interface cards down at the data link layer. The big challenge is figuring out how to seamlessly translate that temporary logical state into a permanent physical fingerprint just so the packets can actually reach their intended silicon.
And that is exactly where ARP swoops in to save the day. Defined way back in RFC 826, the Address Resolution Protocol is the vital translation layer between the network and the data link layers. See, whenever a host has the destination IP but doesn't have the required physical MAC address, ARP resolves that mapping for us. Honestly, without this extremely precise resolution step, communication across your entire local network would just completely freeze up, dead in its tracks. Now, there is a catch, a pretty strict boundary to this protocol. ARP is highly localized. What that means is it functions exclusively within your immediate local area network, or broadcast domain, basically your digital neighborhood. It is definitely not routing anything across the internet. It's strictly designed to resolve addressing within the local subnet you're currently connected to, making sure those logical paths match up with physical hardware for your immediate neighbors.
So how does this handshake actually work in practice? Well, imagine standing in a crowded room. Step one is the broadcast request. It's essentially a device shouting to the entire network, "Hey, who has this IP address?" Every single host on the subnet hears and processes this, but only the specific target IP actually responds. Then, in step two, the target quietly sends a unicast reply directly back to the requester saying, "I do, here's my exact MAC address." Finally, for step three, the requesting device saves that mapping to its cache for future use, and boom, the circuit is complete.
Now, to keep the network from constantly shouting at each other and getting totally congested, devices rely heavily on something called the ARP cache. This is a really clever, rapidly updated local storage table that temporarily logs those recent IP to MAC resolutions. Because IP addresses change all the time, these entries have a pretty short time to live. They expire frequently. It's a genuinely elegant design because it perfectly balances rapid local access with strict network accuracy.
The security vulnerability, the dark side of a trusting protocol. Let's shift gears and look at how this highly efficient system carries a rather significant architectural flaw. The absolute fundamental vulnerability of ARP is that it's inherently stateless. It relies entirely on trust. There is literally no built-in authentication mechanism whatsoever. Because of this, a bad actor on the network can easily execute what's known as ARP spoofing or poisoning. By broadcasting forged ARP replies, they can map their own physical MAC address to a legitimate IP, like your router's default gateway. And your machine? Well, it just blindly accepts this and updates its cache. This results in a silent man-in-the-middle attack, where the attacker is effortlessly intercepting or altering all your traffic without triggering a single alarm. Crazy, right?
But despite those risks, beyond just the basic translation, ARP actually has some incredibly cool variations engineered for specific advanced network setups. Take proxy ARP, for instance. This allows a router to step in and answer requests on behalf of a machine that's in a totally different segment. It enables seamless communication across subnets without the host needing any complex routing tables. Then you have gratuitous ARP. This is basically an unprompted broadcast where a device announces its own IP address. It's super useful for checking to make sure nobody else is using that IP to avoid conflicts, or for updating network switches instantly when, say, a failover occurs and a MAC address suddenly changes.
I'm going to leave you with this provocative thought to ponder. how much of your secure, daily digital life actually relies on an inherently trusting, stateless protocol that was built literally decades ago. Every single time you connect to a local network, you are balancing the sheer incredible efficiency of this invisible translator against the fundamental security vulnerabilities of its trusting nature. It really is the invisible, fragile glue holding modern networking together. Well, thanks so much for joining me for this explainer today. Make sure to keep that silent translation in mind the very next time you hop on Wi-Fi. Catch you next time.
Thanks for watching.